Today, I would like to cover how we make amines, which is a little bit tricky, and also some ideas on reactions of amines, what amines do, what you can do with them once you have them. And I'll just do a spoiler alert there. Not a whole lot. Amines are actually not terribly reactive. They're best known as bases, as they're moderately decent organic bases. But the best way we have to make amines is to take either ammonia or a primary or secondary amine. And we defined primary, secondary, and tertiary amines last time. So it has to be a compound with a nitrogen with at least one hydrogen still attached. If the amine is tertiary, it's not going to work because we need to be able to pull that proton off with a base. And we're going to use a large excess of the ammonia or the primary or secondary amine. And I'm just giving you the generalized case here. We'll do a few examples also with particular compounds. But we need to use a large excess of either ammonia or the primary or secondary amine. And we'll get to why that is, in addition to my pointing out that that phrase might sound a little familiar. Like there was a time recently when maybe I stressed very hard that you had to use a large excess of a certain organic starting material. And the reasoning is going to be very much the same. So what we're going to do with this large excess of the amine is add a little bit of some alkyl halide, preferably primary, preferably of the type alkyl CH2X, where X is either chlorine, bromine, or iodine. You can maybe get away with one of these H's being replaced with another alkyl group. Maybe we would call that a secondary alkyl halide. But for best results, you really want this to be primary, or better yet, best of all, of course, is if R is hydrogen. Can anyone not hear me? Can you hear me in chat? Well, I think so, because people were responding to me. So I don't know. We're getting yes in chat, which is better than F in chat, though sometimes we go there too. In any case, best of all in many ways is if R is a hydrogen also, and then you have a methyl halide. Those are going to be the most reactive. But for best results, we want this to be at least a primary halide. Well, you know, let's go look at this audio thing. Wasn't I actually supposed to use microphone array, Realtek audio? Try that. Is that better? Or is that worse? Worse for sure. Okay, well, I don't know. It's on the usual settings that it always is. Oh, both were the same? Interesting. You know, who can account for technology? Anyway, once you do this step, you actually wind up with a quaternary ammonium salt. And the way you get this structure, and again, we'll do some examples, is you look at whatever is attached to the halogen over here, and you figure out what that group is. Take the halogen away and stick that whole group without the halogen on the nitrogen, form a fourth bond. All this is in the class notes. I've given you a step-by-step method for how to draw the product. In any case, you get, for a moment, you get this quaternary ammonium salt. But salts are, could be the individual computer audio. Well, oh, you mean the students? Maybe. I've had my share of weird audio problems back home with unrelated things. But anyway, so you get this quaternary ammonium salt. And ionic compounds are difficult to isolate. Normally, we want to isolate a neutral compound. That makes it easier. So we need a strong base to pull that proton off. And it doesn't even need to be stupidly strong. Even something like sodium or potassium hydroxide is more than strong enough. And usually that's added as an aqueous solution. The hydroxide ion pulls off this proton, returns the lone pair to the nitrogen, as you can see over here. And so your product, I think you can figure out OH minus and H plus together make H2O. So you are going to get a water molecule as one of your inorganic products. You'll also get one of these halide ions. So, but that's, other than that, basically it. The major organic product will then be this amine. And if we started with ammonia, in other words, NH3, then we'll have a primary amine here. If we started with a primary amine here, we'll get a secondary amine. And if we started with a secondary amine, we'll get a tertiary amine. And so this reaction is otherwise pretty general, only within the limits that this X is better off not being a fluorine, because carbon-fluorine bonds are a little too strong here. Even chlorine isn't too great, though I would expect it would probably work. Bromine and iodine, or alkyl bromides and alkyl iodides, are better choices. So just to give an example, let's say that we started with ammonia, and we used a very large excess of ammonia. What does the salt do? Well, it's an intermediate. It's not the final product, because we don't want to isolate a salt. Salts are hard to isolate. We want to isolate a neutral compound. You mean, what does this do, this salt? Because it doesn't really do anything. It's just going to wait around for us to neutralize it with base. And then we can isolate our amine. So very seldom will we really want to isolate something ionic like that. Not in organic chemistry. But let's say we started with a very large excess of the amine, and say excess, EXC period. I've also seen XS for excess. It's kind of cute. I'm not a fan, but I've seen it. People will know what you mean. In any case, let's treat this just because we can with 1-bromobutane, or even 1-iodobutane, since I started to draw an iodine. Well, this is going to add a butyl group. So again, you look at your, you look at whatever is attached to the halogen. In this case, it's these 4 carbons, it's a butyl group. And you're going to add that straight onto the nitrogen and make a quaternary ammonium salt. And you're just going to use that lone pair on nitrogen to form that bond. 1, 2, 3, 4, like this. And of course, the nitrogen will then have a plus charge. And incidentally, as I've said, I'm not really going to emphasize mechanism very heavily. I mean, it may make its way to a small extent on the exam. It's not something I'm going to emphasize very heavily. But the mechanisms here are pretty easy to understand. This is actually a mechanism we'll also cover when we get to chapter 6. It's of a type known as the SN2 reaction. So we'll get to that. But it's pretty easy to understand. What happens is the nitrogen reaches out with its lone pair and hits the carbon that has the halogen attached. And then it breaks the carbon-halogen bond. That's not so hard to believe. When you break that bond, the electron pair in that bond goes onto the halogen, and you get a halide ion. You get I-, right? Because you would have started out with 3 lone pairs. On the iodine, this is going to put a 4th lone pair, so you get I-. That's a very familiar species from Gen Chem. And so that's how you get this. That forms this new nitrogen-carbon bond. And then we're going to treat this with usually sodium or potassium hydroxide. It may even just say OH-, because the alkali metal ion doesn't matter. That's only a spectator ion. That doesn't play any role in the chemistry. And that mechanism is also easy to understand. It's just an acid-base reaction. So remember, we use arrows always and only to show movement of electrons, never of atoms, never of charges. So we don't draw an arrow here saying this H goes over here. No, no, no. Rather, the hydroxide ion reaches out with one of its electron pairs and grabs that proton. In this case, it could have been any of these 3. They're all the same. Take your pick. And we'll break that hydrogen-nitrogen bond. We'll put the electrons onto the nitrogen nucleus, and they will then be on the nitrogen, and we'll see them as a lone pair. And so we'll have a butyl group, 1, 2, 3, 4, and then 2 hydrogens. You could just write H2N, CH2, 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 CH3. That'd be perfectly acceptable. So the reaction is done in 2 steps. And again, you do get inorganic side products. I'm only calling this a quaternary ammonium salt because it has 4 bonds to nitrogen. Generally, we do associate real tetraalkyl quaternary ammonium salts with that. Maybe I should just have said that it's an ammonium ion, because it's a nitrogen with a plus charge. I certainly did not mean to make any kind of contradiction. I try my best to avoid making contradictions. Sometimes I screw up a little bit. So let's just call this thing a nitrogen with 4 bonds and a plus charge. Does that help to remove the contradiction? I don't really care even what you call this, but you do get a positively charged intermediate. And we can then get rid of the plus charge by pulling off one of the protons. There may be multiple protons, it doesn't matter which you pull off. So this mechanism isn't terribly heavy lifting. Like I said, I'm not going to say you don't have to know it, but I will say it's not something I'm going to emphasize very strongly. I don't mind mentioning it in cases like this when the mechanism's fairly straightforward. It's just these 2 steps. First, you alkylate the nitrogen using the alkyl halide, and that explains how this alkyl group winds up on the nitrogen. And then there will be at least 1 hydrogen left on the nitrogen. When you add your base in a second step, that base will just pull off one of those protons and you'll get your neutral product. So you'll also get water, and I guess you would also get like sodium iodide in this case, none of which we really care much about. We're more interested in the organic product, which in this case would be butylamine. I want to do at least one more example, but any questions on that one? Well, let's say then, let's just make it a little more interesting. Let's say we started with dimethylamine. And sure, you could draw the 2 methyl groups separately. That's fine. I'm just shortening it for myself here. And let's say that we treated this with benzyl bromide. Oh, again, that horrible term benzyl. Whoops. Which sounds like a benzene ring with a bromine, but it's not. It's benzene ring, then CH2, then bromine. So remember that pH means C6H5. pH means C6H5. It's a benzene ring with exactly one of the H's replaced with something else. And so benzyl bromide is not PHBr, it's PHCH2Br. It's an unfortunate name, but we are unfortunately stuck with it. And of course, we'll assume that we use an excess of the amine. Hopefully, OWL will not be too sloppy about that, but really you should point out somewhere in the problem that you've got a large excess of the amine. And this is a secondary amine, right? Because we have 2 alkyl groups attached to the nitrogen. This will put the benzyl group onto the nitrogen and create a positively charged intermediate. Nitrogen with a plus charge. 4 bonds, no lone pairs, and a plus charge. So we've got NH, and we've got our benzyl group up here. And by the way, if you don't like the abbreviation pH, you can write C6H5, or you can draw up the benzene ring. Both perfectly acceptable. That's how it is with all of these abbreviations. It's not mandatory for you guys to use them. I only expect that when you see them, you understand them, and you know what they're talking about. That nitrogen now will have a plus charge, though honestly, I'm not in love with drawing out that bond. I think it makes it look worse. Because really there's 2 bonds there, so you're better off leaving both of them understood. This is not a big deal, it bothered me. That's a little better. So you get this cationic intermediate, and then in the second step, you add sodium or potassium hydroxide, probably an aqueous solution, and that's going to give you a water molecule plus, let me see now, benzyl dimethylamine. And so we've actually made a tertiary amine from a secondary amine. But as long as you use an excess of the amine that you're starting with, you can use either ammonia or a primary or secondary amine, and your product will be substituted one more time. Having trouble finding a place to put chat. And your product will be substituted one more time than what you started with. And again, the mechanism is pretty straightforward. Your ammonia or amine acts as a nucleophile, kicks off our leaving group, as we will call this. It's understandable. The carbon-halogen bond is fairly weak, and because you generate a nice stable anion, and then you get this positively charged intermediate that then gets neutralized with base, usually hydroxide. There are other bases you can use, but hydroxide is usually the most readily available and convenient. Let's see. What's the name of the product again? I would call this one benzyl. Whoops. Dimethylamine. Because B comes before M, right? And you don't have to give numbers because they're all attached to the nitrogen. So that's what I would call it, and I'd feel pretty confident that's the best name. Good, so that's how alkylation of ammonia and other amines works. That's one way of making amines, and it's pretty much the only way. Oh, I forgot to say, so why are we emphasizing that you need to use a large excess of your starting material? Well, the reason is, let's just look at this one over here with ammonia. So you initially get this stuff that, of course, you deprotonate to get this. But then if you've still got more of this alkyl halide around, it's possible that this amine product could react with the alkyl halide also and give you something with 2 butyl groups and 1 hydrogen. And then maybe again with 3 butyl groups and no hydrogens. So that's the problem. The reason we emphasized it earlier was when we were halogenating alkanes, we were trying to avoid getting products with multiple halogens in them. We just wanted monohalogenation products. Same thing here. In order to prevent it from getting multiple alkylations and just putting one alkyl group on the nitrogen, we need to use a large excess of the ammonia or the amine that we start with. And the principle is exactly the same. So you don't have to learn 2 different things. You're learning just one thing. It's the same idea applied in 2 different cases. The reactions are rather different, right? On the one hand, you've got a radical reaction, and this is nothing like a radical reaction. But the idea behind it is the same. So if you understand one, you understand the other. And same thing over here. Well, actually, here we're starting with a secondary amine. So I guess there you don't really have to worry about it. But certainly if you've got ammonia or a primary amine, then in order to avoid getting multiple products with more than one of the alkyl groups on the N, we need to use a large excess of the ammonia or the primary amine to prevent that from happening. And you can also see why, if we were to start with a tertiary amine instead of ammonia or a primary or secondary amine, we'd get nowhere. You'd get to this point with the intermediate with the plus charge. There then is no hydrogen to pull off, no proton to pull off. So it just goes back to starting materials. So you don't get a reversible reaction that way. But as long as you use ammonia or a primary or secondary amine, you're in good shape. And I think that's about all I can think of in terms of that. I do want to be sure to talk a little about basicity of these things, just so you understand why they're different by so much. And we'll do amines reacting with acids and acylation of amines to give amides. And then that will be enough. Is the amine at the top also a secondary amine? Do you mean in the example over here? It would have to be at least primary, but we don't know what these other 2 things are. If these 2 things are both H's, then this is a primary amine. If one is an H and one is an alkyl group, then this is a secondary amine. And if they're both alkyl groups, then it's a tertiary amine. We defined primary, secondary, and tertiary amines last time, I believe. I'm pretty sure I recall doing that. So does that help for the question in chat? Seems it did. Okay, other questions before we move on to just a little bit on relative basicities, because it turns out that not all amines are created equal. Wait a minute, clear all drawings. And this gets into, again, either base dissociation constants or pKa's of the conjugate acids of these things. Of course, I don't want you memorizing any particular numbers, but there are some trends that pretty much hold steady that I think are worth knowing. And one of them is, other things being equal, alkylamines. Let me just make sure I didn't write this. Oh, I wrote it word for word in the class notes. Other things being equal, I even used the phrase other things being equal. You'd think that I wrote this. Alkylamines are slightly stronger bases than ammonia. So you don't have to worry about having heard me say that. It's written word for word in the class notes. Other things being equal, alkylamines are slightly stronger bases than ammonia. So for example, we made butylamine before. That would be an example of a primary amine. And we can compare that to ammonia, and what we discover is they're both basic, but the alkylamine is a stronger base, not by a huge amount, but it will be consistent. What that means is that this compound is better at taking an H away from an acid, better at taking an H away from an acid than ammonia is. This is a weaker base. And I say H, I'd really rather say proton, but I just want to make sure that everyone understands me. And the reason, what's not hard to understand why. This alkyl group has a lot more electron density around it than a hydrogen does. The only electrons around the hydrogen are in the NH bond. Here you got all of the electrons and all of the carbon-carbon and carbon-hydrogen bonds. So that's now sitting around this nitrogen, dumping a little more electron density onto the nitrogen. That makes this lone pair on nitrogen that much more willing to reach out and react with that, react with either H plus or even with an alkyl group in an alkylation reaction. So it makes it stronger as both a Bronsted-Lowry base and as a Lewis base, both senses. So that's because there's more electrons, more negative charge around this nitrogen that adds electron density around this lone pair and makes it more reactive, makes it happier to react. So that's what's going on there. And I don't know the exact numbers, and I don't expect you to either. I would expect that dibutylamine would be a slightly stronger base still than butylamine, and tributylamine a slightly stronger base still than dibutylamine. That would be my expectation. It would be easy to look that up. Like I said, I sure don't want you memorizing any numbers. The reason you get more electrons around this nitrogen is because there's electron density in the carbon-carbon and carbon-hydrogen bonds that you don't have in just the one nitrogen-hydrogen bond. That makes this lone pair here more reactive because there's more electron density around that nitrogen. So the electrons that are around the N are in these bonds, in the carbon-nitrogen bond, in the carbon-carbon bonds, in the carbon-hydrogen bonds. And that makes this lone pair here that much happier about reaching out and grabbing H plus off of something. But what gives the extra electron density is the electrons in all these bonds that you just don't have in an NH bond. That's at least how I would put it. So I would say that's what you need to know. The more substituted an amine is with alkyl groups, the stronger the base. And it's because you're putting more and more electron density around the nitrogen, making that lone pair that much freer to react, something like that. And again, I won't say the effect is huge, but it's pretty consistent. And I don't expect you to memorize any numbers, but you will find some numbers mentioned in the book, and I think you'll find that pattern pretty much holds true. The more substituted what? I forget what I said. I'm talking more substituted amines. So substituted means things on it that are other than hydrogen. Substituted means things attached that aren't hydrogen. And this is more substituted than this. Butylamine is more substituted than ammonia. And dibutylamine would have 2 butyl groups and 1 hydrogen. That's more substituted yet. So there's your definition. Substituted means things attached that aren't H's. Make sense? And so this is more substituted than ammonia. The dibutylamine would be more substituted than butylamine. Which one is better? The more alkyl groups you have, let me just make sure that I have this in here. Just making sure that I had that in the class notes. So the more alkyl groups you have on the nitrogen, the stronger the base. The more, well, actually, we can do better now. The more substituted the amine, no, let's do it the old way, where I was going to do it originally. The more alkyl groups, now we have to be careful because this needs to be alkyl groups. And we defined alkyl in, I think, chapter 2. Is this helping what I'm doing here to write down what I'm saying to make sure it gets into your class notes? I'm really trying to make this user-friendly. The more alkyl groups attached to N, the stronger, the more basic the amine, the more basic the compound. Or the more alkaline the compound. I'm going to do CPD for compound. And the reason, and I do expect you to know the reason, because it will help you to remember why, the reason is that the more alkyl groups we replace hydrogens with, the more electron density, the more electron rich this nitrogen is. The electrons come from all of those bonds. And the more electron density you put on the nitrogen, the easier a time it has using this lone pair to reach out and grab H+ from an acid. So, and again, this can be measured quantitatively, but I sure don't expect you to memorize numbers. But we do have to be careful that we're talking about alkyl groups. One notable, I can't even say an exception, it's not an exception, but one particular example of a compound that does not have an alkyl group as we defined it on the nitrogen is aniline. So aniline is this compound, aminobenzene. That was one of the monosubstituted benzenes you needed to memorize from chapter 4. So aniline, that structure shows up quite a bit. Now this is a noticeably weaker base than ammonia. And there's a very good reason for it. It's not a contradiction. First of all, a benzene ring is not an alkyl group, the way we defined alkyl groups. So if you go back and look at that, you'll see there's no contradiction. But second of all, the reason for it is pretty easy to understand. Remember we said a moment ago that it's all about how available that lone pair on nitrogen is to reach out and grab a proton off of something. Well, this is a resonance stabilized species, and it's always good to refresh our memories on resonance since it so often explains things. You can draw a number of other resonance forms. I'll show you at least one of them. But you can draw resonance forms. Whoa, that looks awful. That don't have a lone pair on nitrogen any longer. So it will instead have a plus charge. And one place you can put that electron pair is on this carbon. So you get a resonance structure that looks like this. And I think you'll find there's 2 other resonance forms that also put this lone pair of electrons on 2 other carbons of the benzene ring. What that means is this lone pair isn't just localized on the nitrogen, it's spread around the benzene ring. So it's not as available to reach out and grab a proton. It's not localized on just the one atom. And so that serves to make aniline considerably weaker in basicity than any alkylamine or ammonia. And it's a pretty big difference, as I recall. I think it's a factor of about 1 million, if I'm not wrong. So like I said, don't go memorizing numbers, but this is something we can explain very easily. Let me show you another thing, since it's the same exact argument, and then we'll be pretty much done with this type of argument. Let me show you another thing then that's a significantly weaker base than ammonia or alkylamines. What about an amide? And it doesn't even matter here what R is. So if you've forgotten what an amide is, please review that. But amides are compounds of this type. At least that's the way we defined amides. And these two bonds can be either to alkyl groups or to hydrogens. It doesn't matter. Well, amides are also resonance stabilized species. You can draw another resonance form that again takes the lone pair off of nitrogen. And it means that there's a partial double bond character here. Now remember the rules for resonance. They are, you're not allowed to move any atoms. You're only allowed to consider other ways of distributing the electrons. And that's the case here. I haven't moved any atoms. I've just found another valid way to distribute all of those electrons. So we have O- now, and now the extra electron density is on oxygen, which is pretty good. Oxygen's pretty electronegative. So again, remember, this doesn't mean that the structure is flipping back and forth between these two things. There's only one structure that is somehow at all times a mixture of both of these structures. Similarly, this one is a hybrid with this resonance form and the two others. So, so what that means is, again, our lone pair isn't localized on the nitrogen any longer. It's spread out over more of the molecule. And that means it's not as available to reach out and grab a proton off of something. So amides are also significantly weaker bases than amines and ammonia, other things being equal. And it's for the exact same reason as for aniline. Back here, we were just talking about alkyl groups, and that's always going to be the same here. Methyl, ethyl, propyl, isopropyl, all of your saturated hydrocarbon alkyl groups are going to serve to make the amino nitrogen a stronger base. And we gave the reason for that. But this is not an alkylamine, and this certainly is not an amine at all. And so that's why this doesn't contradict what we have up here. We're talking about different things. And again, I don't want you just memorizing this one's less basic than ammonia. I would like you to understand why, because if you understand why, then you can remember. And it's not just a matter of memorizing a sentence, because as we all know, God knows I know this too. I was in college once, 3,000 years ago, but I was there once. And I know just as well as anyone else that if you memorize something, you can very easily unmemorize it under the stress of an exam situation. So the thing is to understand why it happens. And so that's what I'm trying to show you guys here. Good, I think that's about it for amines and basicity. Let me see what else we've got. I think we need to talk about amines being bases and reacting with strong acids. And honestly, since we have 2 whole days to cover the chapter on nucleotides, that's chapter 18, we basically will have Wednesday and Friday to do that. It won't be the end of the world if I leave that for Wednesday. I do have some reef questions for you guys today. So maybe I'll go on to the next topic. Before that, are there any other questions on this basicity business? So 18 is the next chapter, I believe so. For today, the 28th, we were supposed to start chapter 11. And then next time we were supposed to finish 11 and start 18. And then on Friday, finish 18. So I might just leave at most one topic from chapter 11 for next time. I think we'll then still be fine with OWL. Now let me see. It's still a fair bit out, but our next exam looks like it's going to be Friday, October 9th. So that's not this coming Friday, but the one after. So it should go pretty similarly to last time. I also forgot to mention, I did all the things over the weekend that I said I was going to do. So you'll find on eCampus a document that shows you how to calculate your class grade and also how to calculate what you need to get on future exams. That's all in there. I used that same procedure to calculate estimated class grades for everyone, and that's now also on eCampus. So that includes REEF and OWL and your first exam. And I would not bet the farm on it at this point. I didn't put a lot of stock into it at this point in the term because you've only had one exam. So in order to calculate a class grade for you, I had to assume that you got exactly the same grade in exams 2, 3, and 4 that you got in exam 1. And on the final exam, you got the equivalent grade only scaled up to 200 points from 150. And I think you'll agree, that's a stretch. People generally are not that consistent. So there's room for movement up and down. There's still significant error bars in these calculated grades, but it at least gives you a sense. Are we back? Okay, good. Yeah, I don't know why that. Good. Can you hear me again in chat? Yes, nope. Yes, now. Okay, good. Yeah, I don't know what happened. The mic suddenly went off. I don't know. Well, I'll try to. I've got what? 10 minutes, about 12 minutes. We'll try to finish this up then. Good. So where was I? Oh, so these estimated grades. So I would say a couple things. First of all, check it out, calculate it yourself. I would say if your calculations turn out very different from mine, let me know. I don't think that will happen, but either drop me an email or drop by in office hours. I mean, I calculated them in Excel, and unless extra 40 points on 10. No, I don't think so. Not last time, not this time. There weren't that many. There were some, but not that many technical issues. Basically, I screwed up that one problem, so I'll just try not to screw up problems. But be that as it may. Oh, and of course, within about a week, I should be able to get up not only the topic summary, but also some questions from last year's exam, kind of like you had this time. But in terms of class grade, I'm going to Walmart gift card. No, wait a minute. That's an outright bribe. I don't think I can do that. Will timing be the same as last time? I think so. It seemed to work out all right. Is the final optional? No. Well, everything's optional, right? No, the final is not optional. Final is 20% of your grade, so that's not optional. But anyway. So what else is going to, oh, so I'm going to have to use these, is the final cumulative. Yes, all this is in the syllabus. It says all of this, but be that as it may, I'm going to have to use these estimated grades that I have now for people's midterm grades. If you're one of the students that I report midterm grades, I almost hate to do it, but we're never going to have the next exam graded and done with by the time those are due. They always do it so early in the term. It happens this way every term. My internet connection is now back up. I didn't know it was not up. This looks like it's going to be one of those days. Are you still with us, chat? Because I'm really not so sure any longer. Oh, geez. Thanks, guys. I don't know what all the problems are today. Good. Well, let's just consider one last thing, and then we'll do our REEF session. I have a couple of polling questions for you today. And the last thing I'd like to cover today will deal with acylation next time. It's a way of making amides. But basically the idea is that amines, just like ammonia, they're not terribly strong bases, but they're all right. And any amine will react with any strong acid in order to produce an ammonium salt. And so you know what your strong acids are. You learned HCl, HBr, and HI are strong acids. It's the ones you learned in Gen Chem. You know sulfuric acid's a strong acid, H2SO4. You know nitric acid is a strong acid, although I'd probably be wary about treating amines with at least concentrated nitric acid. You're likely to get oxides of nitrogen out, which is unpocotoxic. So I would go easy with that one. But it shouldn't be any surprise, for instance, if you were asked what the product is of, let's say, ethylamine with HI, hydriodic acid, very strong acid. Well, this is going, the lone pair on nitrogen is going to grab a proton from your acid, and I would expect our product would be the ethylammonium ion. So this now has 3 protons and a plus charge on nitrogen, and of course you'd also get the iodide ion. You can't really get a cation without also getting an anion. So nothing surprising there. Or just to give another example, let's say that we took aniline, which is again a significantly weaker base, but not so weak that it won't react with HCl. HCl is one of the strongest acids that there is. Let me just do one thing. So there's our aniline. Let's react that with HCl. And you can see how it works to figure out the product. Your first step is you add an H to the nitrogen and give the nitrogen a plus charge. And then whatever is left as the anion is your other product. Generally, we don't care so much about that one. We're more interested in the organic product than in any inorganic side products. But so it'll go from NH2 with a lone pair to NH3 plus. This looks like a 7-membered ring. If I don't fix it, it's going to trigger me. And the other ion would be chloride. But the organic piece would be the anilinium ion, which is the conjugate acid of aniline. Or, you know, let's go crazy. Dibutylamine. This could be any primary or secondary or tertiary amine. You learned about this in Gen Chem regarding ammonia. So amines will do the exact same thing. Let's react this guy with sulfuric acid. Well, I would expect that you'd get the conjugate acid of dibutylamine. Just add an H to it and make sure the nitrogen is a plus charge. Leave everything else the same, except I somehow lost a carbon. Wait a minute. 1, 2, 3, 4. Right, this should be a butyl group. Another butyl group on this side, 1, 2, 3, 4. And the other piece will be the conjugate base of sulfuric acid. We go from H2SO4 to HSO4 minus. Which again, we're not so concerned about. Sometimes they'll even leave that out. So this plus this are the 2 species you get. So a bottom line, amines can act as bases, which is nothing terribly new or exciting. But there is one other thing you can do with amines that will allow us to make amides. That can wait till next time. Good. Any other questions then on the basicity of amines? This will help you if Al gives you questions like this. What is the product when this reacts with this? That will help you with that type of question, which I'm fairly certain you will get. Good, so let me change this to the PowerPoint. Please do register your attendance because that's going to be at least 8 out of the 10 points. We'll go to slideshow. Here we go. And then we'll cover that up. Good, so with your Reef polling app, please. And hopefully everyone can see this on Reef. I'll start the timer in a second. Which of the following is a secondary amine? Should be pretty straightforward. Not meant to be a trick question. I don't want to keep you guys too late, so we'll go out to 1.5 minutes. And the answers are pouring in. We're over 100. There's a lot of excitement in the room. Sorry, I'm trying my best. Keep wanting to scratch something I like. All right, say another 25 seconds or so. Last chance, 10 more seconds. Going once, going twice. Anyone else? Looks like we're at 131. Okay, well, if you recall, the definition of a secondary amine is a nitrogen with 1 H and 2 alkyl groups attached. And only E falls into that description. Secondary amines can be cyclic. This one's tertiary. These two are both primary, and that's a quaternary ammonium salt. So I think the best answer is E. Somewhat split. Actually, you just edged out the second best answer, but that, or second most popular answer. But I think E is the best answer. This will wind up on eCampus eventually, so you can review with it. And yes, this is going to work. Actually, I think we did this exact one. But benzyl, or something like it anyway. Benzyl bromide is treated with a large excess of ammonia, then neutralized with base. What is the major organic product? Or a large excess of ammonia is treated with benzyl bromide, then neutralized with base. Same thing. We did this in class today. And we'll go out to 1.5 minutes again, since I don't want to keep you guys late. And of course, the other 8 points will be from attendance. All right, 15 more seconds. All right, anyone else? Last chance. Someone took me up on that. That's fine. Well, remember how we do this. You take the nitrogen of either ammonia or the amine you're given, whatever it is your starting material is with nitrogen, and you put that nitrogen where the halogen is on the alkyl halide. And then, of course, you'll need to remove a proton to get a neutral compound. The result will be benzylamine, as it turns out to be called. PHCH2NH2. That should be what we got earlier today, and I think that's the best answer. So that's C. Yep, overwhelmingly the most popular. Good, so the remaining 8 points are on me. I think we're out of time. Let me just double check that. Yeah, we are. So yeah, right, 55 to 45. Good, so we'll end it right there. We'll finish up the chapter next time and start talking about nucleosides maybe also. So other than that, have a great day. See you Wednesday.